Hi, you are at level 3 out of 30 easy steps to understand everything you want to know about Einstein's theory on special relativity. Have you always been curious what it is all about but feared its complexity or its math? Then this level is for you. Today we will talk about vectors, vector fields and frames of references, and by doing so we will learn how to navigate the storm. GP, hit it! Today we are going to talk about how to navigate a storm when sailing. It will also give us a nice and easy introduction into vectors, vector fields and frames of reference. These concepts are really important when we climb Einstein's mountain. If you're new to the story, my name is Tom and I'm on a mission. My mission is to explain the theory of Einstein's special relativity in 30 easy steps, accessible for everyone. But today we go sailing and play a little bit tennis. Here we have two islands, Island A and Island B. Island A is a triangle and Island B is a square. Why? I cannot draw. So here is a sailboat, and the sailboat wants to go from this port to this port. And what do you do when you go sailing? You check the wind. And the crew did the same. They checked the wind and plotted the wind on their map with these arrows. And each arrow tells them in a specific location on their map the direction of the wind and how strong the wind is. The bigger the arrow, the bigger the wind. And together they are the entire wind field. And if you look at this and you want to go from here to there, it's probably a good idea to go a bit like this. Although time could also change the wind. But for today the wind is static. No changes. It's this all day. And there you have it. These arrows indicate the wind, but they are also called vectors. And a vector tells you the direction and the strength of something, somewhere, sometime. And together they are a vector field. Et voila! You now know everything you need to know about vectors and vector fields. Now it's time to look a little bit more deeper into the concept of a vector. Let's start with its definition. Well, it's my definition, and I'm saying it is a tool that tells you the direction and the strength of something, somewhere, sometime, just as we just saw in the wind field. So, sometime is a time. Somewhere is somewhere in space. And there you have it. Here we see a vector colored red. And mathematicians, they usually give it a letter, here the V for vector, with a little arrow on top of it to indicate it's a vector. It has a length and it has a direction. So now we know the direction, the strength, which is equal to the length. We know the sometime, we know somewhere. So all that's left is something. Let's look at something. Well, we just saw a perfect example. Vectors are really great to describe the flow of wind, where it's going and if it's strong or weak. So that's intuitive. It could also be the flow of something else, like water or syrup or whatever, you know. Could be anything. Trick question. Temperature. Is temperature a vector? Think about it. No, it's not, right? Temperature has a strength, but it has no direction. It's just there, somewhere, sometime, with some strength, but it doesn't have direction. A force, someone pulling you, yep, that's a vector. The force is pulling somewhere at some time and you know the direction, you can feel it. The speed of a rocket. Yep, it's a vector because velocity or speed not only has a length or strength like 80 miles per hour or 100 kilometers per hour. No, it has direction. Yeah. So if you turn, you change the velocity because the vector changes its direction. Time. Is time a vector? I think it's common known that it's a scalar, but who knows, you know? So this is what a vector is, yeah? So it's easy. What is a vector field? Well, a vector field is just nothing else than a bunch of vectors. Direction, strength, something of somewheres, sometimes. You saw in my introduction a little movie, I will play it again here. So here you see the time is changing and you see these little gray dots, those are the somewheres. The clock is giving us the sometime and the vectors change direction and strength. In this case it's a random vector field. I just made them wiggle a little bit, right, for 20 seconds. But that's a vector field. So now we know what a vector is and a vector field. Let's dive a little bit more deeper into the matter and look at the building blocks. So here we have the vector field and we saw it consists of a bunch of vectors, right? What we haven't discussed yet is how vectors are expressed in either components or length and directions, and how vectors are calculated using vector field equations. We will talk about them soon. Vector field equations, they take as input a location and a time, and they produce a vector. The vector at that specific time, at that specific location. Time. Well, time is time, right? Well, we have to be really careful on Einstein's mountain when it comes to time. So we need to define the unit of measurement. Are we talking seconds, hours, days, weeks, whatever? We need to choose. And which clock are we referring to? You always need to know which clock we are referring to. It's very important. Then the location. A location is usually expressed in coordinates. We will also dive into this a little bit more after this slide. And coordinates also use a unit of measurement like meters, feet, kilometers, miles, whatever. And they refer to something called a frame of reference. So we checked vector fields and vectors. Now let's go under the hood. And we check time, unit of measurement and clock. So next we are going to look at this and we are going to look at location. Location is next. Let's start with location. Let's go back to the 80s where we had a great tennis game, Bjorn versus John, and we will use this scene to talk a little bit more about location, coordinates, unit of measurement and frame of reference. So here we have our playing field. The game has stopped now. The ball is somewhere lying still in the gravel and John is arguing with the umpire, of course waving his racket. And Bjorn is looking at it and waiting for the outcome. Now the ball needs to be picked up either by Thelma, Harvey, Brad or Louise. But there's an issue. They cannot see the ball because the sun is shining very brightly this day and they are kneeled down, so they have not a clear view on the gravel. So I need to tell them the location of the ball using a headset, and then they will decide who's going to get the ball. Well, before we start doing this, we need to define some kind of unit of measurement. You know, if I'm going to give coordinates, we need to know what are we talking about. Meters, miles, feet, kilometers, etc. And in this case, we've chosen meters. So let's create a virtual grid of meters on top of the playing field. It's 1 by 1 meters. So now we have done the unit of measurement. Next, go to Louise. Let's see. I'm going to talk to Louise and tell her where the ball is. I'm going to tell her, well, Louise, from your perspective, your point of view, you need to move 8 meters forward and then 7 meters to the left. Well, you can walk directly to the ball, of course, but the location of the ball is 8 meters in front of you and 7 meters to the left. Here we see it. You can just count the number of blue lines. But Louise waits because I will tell all 4 of them whether they should get the ball, yes or no, where the location of the ball is. So let's talk to Harvey. Harvey, for you the same. The location of the ball is 5 meters in front of you and 7 meters to your right. Again, to your right, not to your left, as I said with Louise. Here we have, so the coordinates of the location of the ball, Harvey, is 5, 7. The first one indicates forward, the second coordinate, the 7, means to the right. For Louise, for you it's to the left. Don't get confused. So, and I can repeat this, of course, for Thelma and Brett as well. And well, I think you agree, it takes way too much time and it is incredibly confusing. So we stopped doing this and we said, okay guys, we are going to pick a single perspective. And then we argued whose perspective is the best perspective. But then in the end we said, okay, let's go for the umpire's perspective. So there we go. Let's go to the umpire. From the umpire perspective, the ball is, I think, 7 meters in front of him and 3 meters to the right. But I could also say it's 3 meters to the right and 7 meters in front of him. Or it's minus 3 meters to the left and minus 7 meters forward. So when we define a perspective, we need to define its origin, which is the umpire, but we also need to define the directions and the sequence of the directions you will use. Let me make this a little bit more clear. So here we define the perspective from the umpire in 3 directions. We say, okay, we are going to express any location in the field with coordinates to the right, forward and up. And the first coordinate will be to the right, how much to the right. The second coordinate will be how much forward, and the third component or the third coordinate will be how much meters up. And in this case the ball is 370. So if I now tell Thelma, Louise, Harvey and Brett, the ball is at 370, and they know where they are, and they know where the umpire is, and they know where the origin is, and they know about the directions that we agreed upon, and they know about the sequence in which we tell the coordinate, they can figure out where the ball is and who's going to get the ball. And it's as easy as that. That's the whole thing about location, coordinates, unit of measurement and frame of reference. Now let's repeat some of the stuff I just said. So a frame of reference, FOR, is something you can refer to. That's why it's called a frame of reference. We can refer to it. And it's really helpful if we want to tell other people locations, especially if we can't see each other. Or you can't even see what you are referring to, like the Eiffel Tower or the Statue of Liberty, and I'm on the phone. You know, we need to express the location, and we have many ways of doing it, but we need a frame of reference. It's a perspective. It has an origin, some point O, you can pick whatever you like. And in the 3D world, it has 3 directions. And a direction is called an axis. So we have the right axis, forward axis, and the up axis in this case. Coordinates in a chosen frame of reference, they define the location of something. Where is it? But it needs a unit of measurement. If I say 370, even if you know the frame of reference and you know exactly the directions, you still don't know how much is 3. In this case 3 meters. 7 is 7 meters, etc. So this, I think, should be an easy way to describe locations. But whenever, before I continue, and how do we write it down? I forgot the closing parenthesis, I see. It's like 370. So the first coordinate, the number of meters to the right, then the number of meters forward, and then the number of meters up. That's how we write it down. And then came along, not a spider, but an evil mathematician. Here he is. He has been with us from level 1. If you want to know more, go see the previous levels. And of course he doesn't want to use to the right, forward and up, because that would explain exactly what the directions are. No. Let's use X, Y and Z. Why? I have no clue, but that's what they do. So they call these axes the X, the Y and the Z axis, or sometimes the ABC axis, or whatever they feel like, as long as it's not understandable for normal people. And when they write down a location or a variable location, they write down X, Y, Z. And you have to know that's probably the coordinates of a location somewhere. And that's what it is. More on vectors. The second thing we said, okay, now we know how a location is expressed. Now let's look at the vectors themselves. There are two ways to express a vector. Either by describing its components or describing its length and direction. Let's see what I'm getting at. Components, method number 1. When you have a two-dimensional vector, like here on the screen, it's flat, then if I give you two components, in this case Vx and Vy, and you draw them perpendicular to each other, starting from the black dot, which is a location, we just talked about locations and coordinates, it's defined, then you can draw the vector. The location, you move to the location and then you draw Vx and Vy, which are the components. And the Vx is in the x direction or to the right direction, and the Vy in this case is, in this screen it looks like it's going up, but in another perspective it could also mean forward, depending on whether you're on the top of the screen or in the field. If you have a three-dimensional vector, you need three components, right? And it's probably Vx, Vy and Vz. So this is easy. If you have those components, you can draw the vector. If you have the vector, you have its length, which is the strength of the quantity you are looking at, and you have direction. It's pointing somewhere. The other method, number 2, is expressing the vector by its length directly and its angle, its direction by looking at its angle it's making with the horizontal in this case. So in a two-dimensional world, if I would give you length and I would give you alpha, which is the the angle between the horizontal and the vector, you can draw the vector. First you go to the black dot, remember, a location, and then you draw the vector using alpha and length. And in a three-dimensional world, usually we have two angles and one length or something else. I mean, it's not really important, it's just important that there are different methods of describing a vector. And on Einstein's mountain, we will use method 1 most of the times. Then, how do we calculate these vectors? Well, we use vector field equations. Here they are. In goes a somewhere, the coordinates x, y and z. A black dot goes into the magic blue vector field equation box. And we put in some time, right? Because vectors can be depending on time as well. So we pick some time. And then in the box, and we will see some examples later, we will calculate the components using method number 1. We will calculate the components of the vector. And out comes the vector at that specific somewhere, x, y, z, and that specific time, t. So this is all there is to it. I think we have discussed all the building blocks of vector fields and vectors, and you are ready to go to the next level. But first, let's look at some examples. Vector field visualization. Here I have an example of a static vector field, and with static I mean time is not an issue. It's always the way it is right now, all the time. We see colored vectors and we see white lines. And let's talk about a little bit more about those. Those white lines are called flow lines, and they express how, well, let's say this is a wind field and we have a bunch of leaves that were fallen from a tree. The flow lines will indicate how the leaves will be, how they will flow through the wind field, how they will flow through the vector field. And you can choose whether or not you want to have flow lines in your visualization. The same for the vectors. You could stick to flow lines only and remove all vectors. In fact, in physics, they usually only draw the flow lines and they just leave out the vectors. You have to know this. You can also color code the vectors, yes or no. In this case, I color coded them, so which means that red is really strong and green is a really weak vector, a small vector. Scale cheating. Whenever you see a tutorial on vector fields, they will tell you that if you do real vector fields with real vector field equations, the vectors get too big, too large, and they clutter the image. So then you have to scale down the big vectors a little bit to make it a nice presentable image. I did this in this one as well. The red arrows, if I would have drawn them on true scale, they would have be out of the window, you know, they would not even fit the image. So I scaled them, and that's why I introduced colors to emphasize they are really big. This is also a nice one. Most of the time you will see that the locations chosen where to plot your vectors on a map is a grid, an evenly spaced grid. But you can also, of course, plot them on the flow lines, which is much more intuitive, but I don't see many people do that. It's usually a grid. Then there's something called isoclines. I did not put them in here. It's where the direction of the vectors is the same and you connect all the vectors with the same direction, no matter about their strength or length, just the direction. And those points, if you connect them and you draw a line through them, that's a isocline, a similar cline, inclination, similar slope. I don't find it very valuable, so I left them out. And I'm sure there are other ways to make vector fields visually attractive. Then one more thing about the evil mathematician. I introduced flow lines. Well, a mathematician will never speak about flow lines. No. Oh, I was too soon. One step back. So here you see what I did. Yes, I did flow lines, vectors, color shading. I cheated with the scales. I did not use the grid. I put the vectors on the flow, and I did not include isoclines. So the flow lines. An evil mathematician will say, we prefer to call the flow lines integral curves. I'm just going to leave it at that. You can make up your own mind about these people. In this case, I go two-dimensional, so I leave out z, and I go static, so I leave out the t for time. This is a very common vector field. In goes a somewhere, in this case 1, 2, and out comes a two-dimensional vector, in this case 2, minus 1. And the vector field equations are really simple. It says component number 1, Vx, is the same as the y-coordinate of the somewhere that was input. And the y-component of the vector is minus the x-coordinate of the somewhere. So if you put in 1, 2, you get back 2 minus 1. Can you follow? Let's do this visually. Here we have a grid, an x-axis, a y-axis. The red lines are x steps, the green lines are y steps. So the somewhere is one step in the direction of red and 2 steps in the direction of green, which gives us the gray dot of the somewhere. Then we draw the vector from that point, and the vector is 2 components. It's 2 steps in the x direction and -1 step in the y direction. So it goes to the right and not up, but down, because it's -1. And there you go. You have drawn and calculated your first vector with a vector field equation. I strongly recommend you try to do this yourselves as well at home. Just take a piece of paper and try to draw this vector field for different points. I did here a few others as well. You will learn quickly that vectors become really large. Here the third vector is really large, and then you will probably start to cheat on the scale. But you know, just do this for a huge, well, not very huge, but a well-balanced grid, and then you will see magic of this simple vector field. Now another example, we go 3-dimensional and we add time. I made up these vector equations. They are totally ridiculous. They do not represent anything. It says the first component of the vector Vx, I named it here Q, is x plus y plus z plus t. Just add all the inputs together. The second component, Vy, which is r in our case, minus x plus y plus etc. And the third component, Vz, is x multiplied by y multiplied by z multiplied by t. So in goes a location, let's say 1, 2, 3, a time, let's say 2 seconds, and then you can do the math. Out comes a vector with 3 components, 8, 6, and 12. Let's see this in action. And because it's 3D, it's really difficult to draw, so I made an animation. The white arrow is our vector 8, 6, 12. It starts at 1, 2, 3 and it ends in 9, 8, 15. The colored arrows here are just the projections of the vector on the different planes. So the yellow arrow here is just the shadow of the white one if the sun would shine from the top. Is it magenta? I think it's magenta. This color here is the shadow of the vector if the sun was coming from the right, and I think this is cyan. This is the shadow of this white vector when the sun would come from the left. So this is how it looks in 3D, and because it's really difficult to do this in a flat visualization, we usually stick to 2 dimensions. So there you go. Congratulations! Vectors, vector fields, and frames of reference.